Okay, so today we will see uh, a slightly different model for communication complexity and called one round communication complexity, and we will prove a lower bound for um, a problem called index, a function called index. So, what is one round communication complexity? So, in the models that we have seen till now, we don't restrict. The only thing that we are concerned about is the total number of bits communicated between Alice and Bob. So this in one round communication complexity, uh, we are not only bothered about the total number of bits communicated, we are also going to not allow this back and forth. So the model is that Alice will send something to Bob, and then Bob will send the answer. That's it. So there is no repeated back and forth that is going to be permitted. So we are placing an additional restriction. So therefore, this the complexity will also it will be at least the complexity without this restriction, right? So we are not allowing this back and forth, and we are insisting that it has to be done in one round alone, right? So this is indicated as D subscript superscript 1F, the cost of the best one round protocol for F. And similarly, there is D1, comma Bob F, where Bob sends the first message, right? But we will not be using this notation. And similarly, the superscript 1, where R superscript 1 indicates the one round randomized protocol. So it may use some randomness, but the communication has to be one round. Alice will send something, and then Bob has to send the answer back. So, very easy exercise to begin with. So consider the function f and the matrix corresponding to the function, let's call it mf. Suppose there are t distinct rows for this matrix, right? There may be many rows, but there are only t distinct rows. So some of the rows could be equal to each other. In such a case, the deterministic one round complexity of the function is equal to log t plus 1, log to the base 2, log t to the base 2. Why is this? So the upper bound is easy to see. So one feasible protocol is Alice. So there are t different types of rows. They both Alice and Bob can label the rows. Okay, this is row number 1, this is row number 2, and so on. And as far as the function evaluation is concerned, Alice just has to identify which type of row she is holding. So she just sends to Bob which type of row she is holding, and Bob just sends the answer back. So to describe which type of row she is holding, she needs to use log t bits. So that is the upper bound. And the lower bound is a straightforward pigeonhole argument. So Bob needs 1 bit for the answer. So now how do we get log t? Because if they use anything less than log t, then there it will so happen that for two different types of rows, for two different types of rows, Alice will end up sending the same message to Bob. And when these two different types of rows are there, because there are two different types of rows, they should differ in at least one position, one column, at least one column. Now, if Bob's answer depends on that one column, now or the Bob's input could be that column. So in that case, he will not be able to distinguish between these two rows, and hence he will not know what to answer. So hence Alice requires to send log t bits, and Bob needs 1 bit. So that's why this is T1F is log t plus 1. Okay, I'm not written down the answer, but I've kind of told you everything. So what is the function index? The function index is Alice is given an n-bit vector, n-bit 0 1 vector, and Bob is given an integer from 1 to n. So the square bracket n denotes the set 1, 2, 3, 4 up to n, the first n natural numbers. Index n is nothing but index x comma I is nothing but the ith bit of the input x. So x is an n-bit vector, and Bob holds an integer from 1 to I. Index is just the ith 1 to n. Index x comma I is nothing but the ith bit of the x, the input that Alice is holding. Okay. And today we will see that the one round complexity of index is linear. It is at least linear. And clearly it is at most linear because Alice could just send her an entire input to Bob. And that is since she's holding an n-bit input. That's a deterministic algorithm. And we have already seen this in the proof of the unary subset sum problem, where it was used that the randomized, exactly this theorem that we are stating here, randomized one round complexity of index is linear. This was used in the proof of the unary subset sum problem, the lecture that Karthik sir had taken. And what are we going to use to prove this? We are going to use the Yavo's lemma, which a variant of which we had seen. So we had seen that the randomized complexity, the with public randomness, is equal to the max amongst the distributional complexities, where the max is taken over all the possible distributions. Now it's the same thing, except that both in the left hand side and the right hand side, we have the one round variance of the complexity. So in the left hand side we have the randomized one round complexity with public randomness and error parameter epsilon, and the right hand side we have the randomized one round distributional complexity protocol, where the max is taken over the distributions mu and the error parameters epsilon. So the proof is exactly the same proof as what we have seen, where we did not have this one round. So I'm not really going to go into the proof. It's exactly the same argument. If you're interested, you could just write it down for yourself. So this is what we will use this result to show the randomized one round complexity of the index lower bound. Okay, we will use this and this. So what we will do is we will show a distribution mu such that the one round distribution complexity under that distribution is linear, or it requires linear. So how? We'll show that any deterministic one round protocol that uses at most Cn bits. So in our proof C will be 0.1. Anything that uses less than 0.1 or at most 0.1 bits has error at least 1 over 8. Okay. So which means that if you want to get error 1 over 8, then you need Cn bits where C is 0.1, which means the randomized complexity of index with error 1 over 8 is linear. And notice that this also implies that, now you may think that 1 by 8 is smaller error than, let's say, 1 by 3. So perhaps for 1 by 3 we may be able to get a linear protocol, a protocol with linear complexity, if we allow for a bit more leeway in the error. But the answer is no, because if we had a protocol with 1/3 error, then we can use boosting. We can repeat and use Chernoff bound argument to show that there exists a 1/8 error protocol by boosting it, which means that and it incurs only constant blow up in the cost. So if the 1/3 error protocol is linear, the 1/8 error protocol also will be linear, but which we know it's not possible. Or if 1/3 error protocol is sublinear, 1/8 error protocol is also going to be sublinear, which we know is not going to be possible. So even this is not going to be possible. So in fact, any randomized complexity. So that's why for any epsilon, any constant epsilon, it's not. It requires linear complexity. Any one round randomized protocol requires linear complexity. Fine. So what's the distribution? Again, we'll show a distribution where this is true. What is the distribution? The distribution is nothing but the uniform distribution over the inputs. So Alice's input is a n-bit string, and Bob's input is an integer from 1 to n, 1, 2, 3, 4 up to n. So the uniform distribution means Alice is equally likely to get any of these n bit strings, and Bob is equally likely to any of these n numbers. Right? That's the uniform distribution. So it's a set, and anything in this set is, so there are like pairs, right? So any pair is equally likely. There are 2 power n times n entries, and each entry is likely to occur with probability 1 by n times 2 power n. Anyway, so consider a protocol P that uses at most Cn bits of communication. Now, C again, recall we'll set C to be 0.1. So think of it as something that is smaller than 1. Okay, Cn is something that is smaller than 1. Alice's input is of n bit length. Now which means Alice can send at most n bit, Cn bit in message to Bob, because that is the total communication that is permitted. Now let us say there are 2 power Cn, so for each Cn bits, since Alice is going to communicate in binary, there are 2 power Cn possible messages, at most 2 power Cn possible messages that Alice could send to Bob. Right? Now let's say Alice sent the message Z. Whatever string that Alice sends, we call it Z. And let's say Bob's input is I. The input that was given to Bob was I. Right? Now, when Z is something, for I equal to 1, again, it's a deterministic protocol. Right? So for I equal to 1, Bob will output a certain answer. For I equal to 2, Bob will output another answer for a fixed Z. For I equal to 3, Bob will output another answer. So you can, for a fixed Z, you can consider the different answers that Bob outputs for I equal to 1, 2, 3, and so on up to I equal to n. So for each Z, for a fixed Z, you can consider this n bits that the outputs that Bob is going to make for that Z and I equal to 1, for that Z and I equal to 2, and so on to that Z and I equal to n. Now these n bits, we can consider it as an n bit vector, and we'll call it A of Z. So it's a function of Z, because once Z is given to Bob, these responses of Bob for each of these i's that he is holding is determined, because it's a deterministic protocol. Hence it's a function of Z, and we call it AZ. So since there are 2 power Cn different Z's possible, because that is the number of, Cn is the number of bits that Alice can send to Bob. There are at most 2 power C, for each Z, we will have a fixed AZ. So there are 2 power Cn such answer vectors AZ that is going to be possible. Right? Just to recap, since the amount of bits that Alice can send to Bob is Cn, there are 2 power Cn messages that Alice can send to Bob, at most 2 power Cn messages. For each such message Z, we can construct the different answers that Bob is outputting. Collecting the different answers, we make the vector AZ. So this is entirely dependent on Z. Right? So now since there are 2 power Cn different possible Z's, that gives us at most 2 power Cn different possible AZ's. Right? So now let us see, for a fixed X and Z, let's say once we fix X and Z, what is the probability that the protocol makes an error? Okay, the probability is over, so X and Z are fixed. The probability here is over the different i's possible. Okay, again recall that the i's are uniformly distributed from 1 to n. So what is the probability that if I equal to 1 there is an error, I equal to 2 there is an error, and so on, and we take their average. Right? So that's why the denominator n. So let's say X was this, the top row 1 0 1 1 0 0 0 1 1 0, and once you fix a Z, the AZ is also fixed. Right? AZ is which means for a fixed Z, If the I is 1, Alice, Bob will output 1. If I is 2, Bob will output 0. I 3, Bob will output 1, and so on. So notice that there are two positions where Bob's output differs from Alice's output. So if the I was 1, 2, 3, 4, 6, and 8, there will be not an error. There will not be an error. If I is equal to 5 or 7, there will be an error. So there are two values of I for which there is an error. So the probability of the protocol being incorrect is 2 divided by 8. In other words, you look at X, you look at AZ, how many bit positions does it differ? So here they differ in 2 bit positions. And that divided by the total number of bits is the probability it will make an error. Right? So given X and AZ, how many bit positions does it differ? And this thing is called, the number of bit positions where two vectors differ is called the Hamming distance. So that is called Hamming distance, denoted D subscript H of X comma AZ. It just means the number of bits in which X and AZ are different. It's called Hamming distance. So the probability that once X and Z are fixed, the probability that the protocol is incorrect, where the probability is over I, is Hamming distance of X and AZ divided by N. And we will now show that if we take, okay, so we have to show that if over the entire distribution of inputs, which means overall X and I possible, the probability that P is incorrect is large. So we'll show that the probability that P is incorrect is at least 1 over 8. Okay, which is what we said here. We'll show that the deterministic one-to-one protocol has error at least 1 over 8. So the probability that P is incorrect at least 1 over 8. How? Okay, so let us consider, so once X is fixed, right, Alice's input is fixed. Since it's a deterministic algorithm, we know there has to be some mapping to what Z she will send to Bob, right? What Z vector. So Z is going to be entirely dependent on her input. And once Bob receives Z, his response is collected as an answer vector A of Z. So A is only dependent on Z. So we can write A of Z because A is a function of Z and Z is a function of X. So let us collect all the possible answer vectors that are going to be output by this protocol. How many such answer vectors are there? We know that ZX is going to be, we are not going to, the number of different messages that Alice is going to send Bob is upper bounded by the number of bits Alice is going to send to Bob is upper bounded by at most Cn. So the number of messages, number of Zs is going to be at most 2 power Cn, and hence there are at most 2 power Cn A of Z possible, and hence that is the upper bound of the size of the set. So size of A is at most 2 power Cn. So here you see the issue, right? Now this means that since Alice's message to Bob is going to be restricted to 2, and in a message of Cn bits, C is 0.1, Alice will have to use the same message for multiple of her inputs. Right? For several different inputs, she will have to use the same message to Bob. And now when Bob is going to say once Bob gets a Z, he is just going to make an AZ out of it. Whatever he makes, now potentially many messages are going to be mapped to this particular AZ, and it is likely that when many messages map, it is not all of them can be close to this in Hamming distance wise, right? So given a vector, we can only have, if you limit the Hamming distance, there are only so many other vectors which are close to it in the sense of Hamming distance. So that will force the issue. That will cause the issue, because the number of the response that the message that Alice sends to Bob is limited in size, Bob will have to make errors, big errors in some of the inputs, and that is going to be the essence of the proof. Okay, so now some definition. Let us say now we have defined the set A, which is a set of answer vectors. So now let us consider just the set of universe of answer vectors in the space. So these answer vectors are n-bit vectors. Now we say that a vector x, the input x is good. We say that an input x is good if there is an answer vector close to that x. What do I mean by close to that x? I mean the Hamming distance between x and the answer vector should be at most n by 4. Right? So if in the space consisting of all the answer vectors, if x is close to some answer vector, if there is some answer vector that is close to x, when I say close, it means at a distance n by 4, we say that x is good. We say that x is bad if all the answer vectors are at a distance at least n by 4 from it. Right? If x is bad, that means every answer vector that you take is far away. None of them are close. Right? So the claim here is that for c is equal to 0.1 and n sufficiently large, more than half the x's are going to be bad. So at least 2 power n minus 1 x's are going to be bad, which means that there are 2 power n x's possible and more than half of them are not close to any answer vector. Okay, that is the claim. So we'll continue the proof of the theorem by using the claim, and we'll prove the claim after this. So what is the probability? The probability ranges from the choice of x and I that the protocol is incorrect. So let us split it into two cases. What is the probability that x is good? So either x is good or x is bad. Right? We know that there are at least 2 power n minus 1, at least half x's are bad. So the probability that x is good, and then the probability that p is incorrect given x is good, or the probability that x is bad multiplied by the probability that the protocol is incorrect given x is bad. So what we'll do is we want to say that there is some fraction of incorrect answers. So this is a probability, so this is at least 0. So we'll lower bound it by 0. And this part, what is the probability that x is bad? We know that x is uniformly distributed over the 2 power n vectors, and we know that there are at least half of the x's are bad. So the probability that x is bad is at least half. And given x is bad, what is the probability that p is incorrect? Given x is bad. Remember, what is the definition of x is bad? If x is bad, it is at least at a distance of n by 4 away from all the answer vectors. And what is the probability that p is incorrect? It is the Hamming distance divided by n. So if the Hamming distance is at least n by 4, the probability that p is incorrect is at least 1 by 4. So for a bad x, the probability that p is incorrect is at least 1 by 4. Hence, this term is lower bounded by half times 1/4, which is 1/8. And the first term is lower bounded by 0. It is something, but we just take the trivial lower bound of 0. So you get 0 plus 1/8, which is equal to 1/8. So now we have shown that with the help of this claim, we have shown that the probability that p is incorrect is at least a constant, and which is what we wanted to show. We said that for a particular distribution, for c is equal to 0.1, we will show that it has error at least 1/8, and that's what we want to show, and that's what we have shown. So maybe I will just recap. So for each input x, okay, we already recapped this part. So for each input x, let the there may be a so for each input x, Alice will send a vector z to Bob, and there are at most 2 power cn such vectors possible, vectors z possible, and for each z that Bob gets, he will construct an answer vector az, right? So since there are at most 2 power cn z's possible, there are 2 power cn answer vectors possible. So let's say A is a set of all these answer vectors, and A is obviously the size of A is upper bound of 2 power cn. And now the probability of the protocol being incorrect, where the probabilities over I is given by the Hamming distance between the x and az divided by n, right? And we say that x is good if there is some answer vector that is close to it. Close to it means n by 4 Hamming distance or less, and bad if every answer vector is at least n by 4 away from it. So when it is bad, then if x is bad, then whatever answer vector Bob is going to say, the probability of error is going to be at least 1/4, because the numerator is going to be n by 4, so the probability of error is going to be at least 1/4. And we are going to see that for c equal to 0.1 n is greater than 300, at least 2 power n minus 1 bad x's, which means at least half x's are bad. Hence, the probability that p is incorrect is the probability that x is good times the probability that p is incorrect given x is good, plus probability x is bad times the probability that protocol is incorrect given x is bad. So this we ignore, and this, the probability that x is bad is at least half, the probability that protocol is incorrect given x is bad is at least 1/4. So you get probability of being incorrect being 1/8. And that completes the proof of the theorem. What we have left is the proof of the claim. Okay, the proof of the claim, I kind of alluded to it already. So the problem is that Alice can only send 2 power cn different possible z's, because Alice's output or message to Bob is restricted to cn bits. And however you arrange these things in the space, you cannot make it close to every possible input vector, right? Why? Because consider an answer vector and consider all the input vectors for which this answer vector will make the input vector good. So for a fixed answer vector small a, now how many x's does this a make good? So by that I mean how many x's are at a distance at most n by 4 from this. So that is the number of x's which are made good by this a. And we are going to show that this is going to be not so high. And hence the total number of answer vectors possible times the number of input vectors made good will still not span the entire thing. So what are the input vectors that this makes good? It is those input vectors that are at a distance at most n by 4. So first one input vector is a itself, then the input vectors which are at a distance 1 from a, at a distance 2 from a, and so on till at a distance n by 4 from a. When I say distance, I mean the Hamming distance. So how many vectors are there at a distance 1 from a? So you can pick any one of the n bit positions, the indices, and once you fix a bit position, then all you can do is just flip that bit, right? So there are n choose 1 vectors which are at a distance 1, and n choose 2 vectors which are at a distance 2, because you can pick 2 bit positions, and n choose 3 vectors which are at a position at a distance 3, and so on till n choose n by 4. Now this particular summation is upper bounded by n times 4e whole power n by 4. Why? This is again our friend Stirling's approximation. In fact, it is a simpler version of Stirling's approximation. So Stirling's approximation gives us, or it's a looser version of Stirling's approximation. It gives rise to this bound. N choose k is upper bounded by en divided by k whole power k. And in this summation, the biggest binomial coefficient is n choose n by 4. So we will upper bound each term by n choose n by 4, and n choose n by 4 is upper bounded by, if n is n and k is n by 4, it is just 4e whole power n by 4. So every term is upper bounded by 4e times 4e to the power n by 4, and there are n by 4 plus 1 terms, but we just don't care. We have enough leeway, so we just write it n times this. So, but because this is enough, I could have written n by 4 plus 1 times this, but it's a bit inconvenient, and this works. So it's upper bounded by n times 4e whole power n by 4. So these are the vectors, input vectors x, that are at a distance n by 4 or less from A. Right? Now I can write this n times 4e whole power n by 4. I can write it as 2 power log 4e times n by 4, and this thing is roughly 0.861 times n. So notice that the by 4 also taken into account. And this is the number of good inputs that are created by A. How many x's are made good by this A? This is given by this. Now, what is the upper bound, or what is an upper bound of the total number of good inputs? The size of A times this. Notice that if I have two A's, perhaps maybe some input x is close to both of them, in which case there is an intersection between these two Hamming balls around the vector A, in which case it will there will be intersections, and this then total number of good inputs will be less than this. But let's anyway, we know the worst case is that all of them are disjoint, and the total number of good inputs is given by size of A, and for each element of A there are this many x's that are made good, so times this, and I can write A is upper bounded by 2 power cn, right? A is upper bounded by 2 power cn. So I write 2 power cn here, so that gets taken, absorbed here, 0.861 plus c times n, and this n is here. And now it is easy to check that when c is 0.1, so you will get 0.961 here, and n is at least 300. You can calculate. You can use Wolfram or Google calculator to check that for these numbers, for this situation, this thing is going to be at most 2 power n minus 1. So I checked it, and I got this thing was something like 2 power, for n equal to 300 and c equal to 0.1, this thing was something like 2 power 296 or something like that, which is less than 2 power 299, right? Anyway, so this upper bounds the total number of good inputs, which means at least the remaining ones are bad. So the proof of the claim is clear. All that we do is we consider for each vector in A, we check how many inputs can it make good. So these are called Hamming balls. The points that are around A that are at a distance n by 4 or closer. So we can think of it as Hamming balls. So the point is that even if you have this n by 4 radius Hamming balls, you can only cover at most half the inputs. That's what we just showed. So there are at least half the inputs which are rendered bad because they are not covered by any of the inputs. So that's the gist of this proof of the claim. And finally, I just want to state one other result. We have seen that disjointness, the lower bound is square root n, and I also remarked that the lower bound, there is a linear lower bound, but I have not shown that in the class. But here for the one round lower bound of disjointness, there is an easy lower bound, using easy as in now that we have shown the lower bound of index, the one round lower bound of index, the disjointness lower bound follows easily. Why? Because we have shown that the index randomized, one round randomized complexity of index is linear, right? So we can reduce index to disjoiners. So which means that index can be solved if disjoiners can be solved. So if disjoiners has a linear protocol, then index also has a linear protocol. But so disjoiners cannot have a linear protocol. Or if disjoiners, if disjoiners has a sublinear protocol, index also has sublinear protocol. Because we know index does not have a sublinear protocol, disjoiners also cannot have a sublinear protocol. So given xi as the inputs for index, we uh, construct the instance for disjoiners as follows. Alice is given x and Bob is given ei. What is ei? Ei is the n-bit vector which is 1 in the position ith index and 0 in all the other indices. So which means there is only one in Bob's input, which is at the ith position. Everywhere else it's 0. So now Alice's input and Bob's input are disjoint if and only if the xi is equal to 0, because all the other positions x, it doesn't matter. If xi is 0, then they are disjoint. If xi is 1, they intersect because Bob's set has only I and Alice's set is disjoint or not disjoint depending on whether her ith bit is 1 or not. So index of x comma I is equal to 1, which means the Alice's ith bit is equal to 1. This happens when x and ei intersect, or the disjoiners function of x and ei is equal to 0. And this is if and only if. If this is 0, this is 1. If index is 0, then this disjoint is 1. Right? So that's what if and only if means. Right? So because there is a direct correlation, so Alice and Bob, if they get this x and I, they can construct this. Bob can construct this instance EA and then try to solve disjointness, but then we know that index has at least linear complexity, so disjointness also cannot be solved in a linear manner. That's the proof. It's like any other reduction, any other hardness reduction. We solve we show that whatever we know or whatever we want to show is hard, we reduce it to a already known hard. Whatever is already known to be hard, we reduce it to the interested problem. If the interested problem can be solved easily, that would imply that the known hard problem also can be solved easily. But this is of course impossible, and hence the new problem is also hard. Okay, so next class. So why did we do all this? So one is it's interesting. The next thing is that next classes, we are going to see streaming lower bounds using index. So we will so this one round is particularly useful in the one-pass streaming protocols. So we have already seen the unary subset sum where communication complexity was used to prove streaming bounds. Now we will see some different type of different streaming bounds using the result that we showed today, which is that the randomized one round communication complexity of index is linear. All right.